Okay, what do we want to achieve with the k8s-gerrit deployment? So it's a way to deploy and operate Gerrit in an automated, scalable, highly available, and self-healing way. That was the vision when we started. Everything is, all the management is based on the Kubernetes operator pattern. So operators are software extensions to Kubernetes that make use of custom resources to manage applications and their components. Operators follow Kubernetes principles, notably the control loop, which is used to ensure that if the system deviates from the desired behavior, it's brought back to the desired behavior. So always the control loop adapts the cluster state to match the requested state. It's listening to custom resource updates. So if you change anything in the cluster configuration, it will listen. It will be notified. The client will update custom resource. For example, an admin changes a configuration, and then the control loop will compare the state requested in the custom resource with the current cluster state and adapt the cluster state again so that it matches the requested state. For Gerrit, we implemented such an operator in the k8s-gerrit project. It helps to simplify the deployment. It has built-in Gerrit application knowledge, so it's specific to Gerrit. It handles configuration of request routing, validation of configuration changes. So if you change configuration in a way which it cannot serve, it will fail the update of the configuration. It manages Git garbage collections, and it's also managing different kinds of updates. The implementation is done in Java because we thought the Gerrit community is using Java for the Gerrit development. Hence, we have chosen the same language also for the operator. And the implementation is based on the Java operator SDK and on the Fabric 8 Java Kubernetes client. At the moment, it's running on Java 21. The former static Helm chart is deprecated, so we don't work on it anymore. And you will also learn why it makes sense to have the operator which can do more things than just a static deployment. The managed custom resources the operator takes care of are first the Gerrit resource. It represents either a primary or replica Gerrit instances. Each of them is a stateful set, so you can scale it up and down. Then there's the receiver custom resource, so that's an Apache server which can be used to receive replication pushes, so that you can set up a separate site which can just serve fetch and clone requests. Then there's a custom resource for the network setup, so it's there to so that you can configure routing of requests. Then there's a cluster resource, which is a set of Gerrit resources and receiver instances plus the Gerrit network. So this is the enclosing entity. Then there's some auxiliary resources. Git garbage collection is used to schedule Kubernetes cron jobs, to schedule Git GC. And there's another similar cron job which can schedule incoming replication if you want to replicate from another Git server inbound. And since a few weeks, there's also a Gerrit indexer resource which manages preparing a new version of the search index. Now, what is a Gerrit cluster? In this terminology, it's a set of scaled specialized Gerrit instances, namely primary and replica instances, which serve a common set of repositories. And they use a single point of ingress for client requests. Now, with that, with these custom resources, you can currently configure the cluster configurations which are mentioned here. So the red number is looking at the legend. In red, it's either a stateful set or a deployment, and the blue one is pods. so individual processes isolated in their own environment. So the simple ones are read-only cluster. So it's just a stateful set of replica Gerrit instances. You can have a receiver cluster which only receives incoming pushes. So this could be, for example, used for just having a backup without serving any Git requests. You can combine those two into a replica cluster with a receiver. So that's useful if you want to have a cluster which just can receive incoming replication requests and serve them so that you can serve fetch and clone requests from that replica cluster. Then going to clusters which have primary Gerrit instances, you can have just an active HA cluster. So one stateful set of at max 2 primary Gerrit instances. And you can have the setup which we use in production. That's an HA cluster with co-located replicas. So it's one stateful set with 2 primary Gerrit instances and one stateful set with n replica Gerrit instances, which can serve fetch and clone requests. Here's a diagram displaying this setup. This is what we are currently using. So we have a cluster of 2 primary Gerrit instances, and we have a cluster of replica instances. They all look at a shared volume, which contains the Git repositories and the web sessions. And also the Git GC cron job can also access those, of course, because otherwise it couldn't run on the repositories. And all that is managed by the Gerrit operator. And at the bottom, you see the ingress provider. There are multiple choices. So what we use is Istio. There's also Nginx is available, and Ambassador was contributed by another company. Now, why split the workload between primary Gerrits and Gerrit replicas? So this is basically a means to separate different kinds of workloads, which can help, for example, the Java GC to be more optimal. So in a way, so that there's less impact on requests needed for the Gerrit UI, which may suffer from heavy fetch or clone requests. By separating fetch and clone requests from the other traffic, we can isolate those workloads from each other. Also, this makes horizontal scaling easier because the replica only needs access to the repositories. There's no need to prepare an index. If you add another replica, it just needs access to the shared volume. When we started the endeavor to provide a Kubernetes deployment for Gerrit, we started out with just a replica cluster, which we connected to our on-prem primary server. So this was the starting point. On the left-hand side, we see the 2 primary Gerrits, which provide HA. And this HA functionality is provided by the high availability plugin. It first needs to discover the other pod. This is done through using JGroups with a Kubernetes plugin. This way, they can dynamically discover each other. And then, depending on which side some change, for example, arrives, index events will be forwarded, cache evictions will be forwarded, and also stream events will be forwarded between the 2 primaries so that they are always in sync. And in order to protect ref updates, there's a global ref database. In our case, this is we use Cloud Spanner. Basically, that provides a means to do ref updates without losing any update. So it's providing logs which are stored in the database, and it also keeps track of all the refs of the participating of the served repositories. Then we have the network part, which is also managed by the operator. So as I already said, we have those three choices. The Nginx ingress controller is what you usually use when you start using Kubernetes, because it's quite simple to start using it, but it's limited. So supporting SSH with Nginx is only partially possible. We then decided to go for Istio because other teams in SAP also use that, and it's very powerful. On the other hand, it's also quite complex, so understanding the configuration is not is an art in itself. And there's also support for Ambassador, which was contributed by Arista, and this only has HTTP support, but not because it's not possible to implement SSH, but it just wasn't done because they only use HTTP. Now let's look at the request routing in the setup we use. So a stateful set of primary Gerrits and a stateful set of replicas. So if a client request comes in, first the Istio will check which protocol is used. If it's SSH, we cannot transparently load balance, so we use two different ports for fetch and clone requests. We use 39418. And for all other kinds of requests, we route them via port 29418 to the primary Gerrits. If it's HTTP, then Istio can transparently load balance because there we can see which kind of request is incoming. So if it's a fetch or clone, the request will be routed to the replicas. And if it's any other request, it will be routed to one of the primaries. Now let's look at the Git garbage collection cron jobs. We use Kubernetes cron jobs for that. So the scheduling is done by Kubernetes. And the operator provides the means so that if you just provide a schedule for GitGC, it will just run GitGC for all repositories on that schedule, one after the other. You can also have additional Git garbage collections resources for specific repositories. So a typical example is all users, which typically needs to be garbage collected quite frequently in order to ensure that performance is good, because all draft comments go there of all the projects. And it might also make sense to have a different schedule for large repositories where there's a lot of traffic. The operator will also ensure that at most one job is explicitly selecting a repository. If you try to schedule two jobs for the same repository, it will reject that to avoid that there's any competition. So this is again an overview over the custom resources I went through. So the Gerrit cluster is the whole beast. Then we have the Gerrit instances. On the left side, the primaries. On the right side, the replicas. We have the Gerrit network, which configures the routing I explained, and the Git garbage collection cron job. I didn't mention the incoming replication task that's similar to the Git garbage collection. Configuration management is also handled in a smart way by the operator, because some of the Gerrit configuration is predetermined by the setup. So, for example, if TLS is enabled, then the operator will automatically set the correct proxy URL. And if TLS is disabled, it will do the same using the proxy HTTP instead of proxy HTTPS. So if you don't set this, you don't need to set those options. The Gerrit operator will set them automatically, but you can also set them explicitly, but it will only accept it if it's matching the expectations of the k8s-gerrit setup. And the most recent addition we did was the Gerrit indexer resource. This can be used if there's a new index schema version where a new index has to be prepared. And for large sites like ours, this can take a long time. That's why we implemented this resource. So the preparation is started by first upgrading the cluster to the new version, which has the code for the new index version. And we set the online upgrade to false to avoid that the new index is prepared by the primary pods themselves, because that would create a lot of additional load on the primary nodes, which could affect the performance of the primaries. So this effectively means we deploy the new version, but we still use the old index in the Gerrit primaries. Then next step, which still needs to be done manually, so that's not yet automated. You need to deploy the indexer resource, which will then start offline reindexing. In our case, this took for the latest change indexes took something like a day to compute it. So this pod will create the new index version, and at the end it will copy it to a shared volume, which is mounted into the pod. And then we still need the support for the Gerrit indexes still requires some manual steps. So you have to then copy the new index version manually into each of the Gerrit primary sites, because the search indexes are per primary. And you need to add the new index version to the Gerrit index config and set ready to false. And then the incremental online reindexing can be configured by enabling the online upgrade. And in addition, you can set the new option reuse existing documents, which we implemented to ensure that the step is fast. So in our case, for the last upgrade, this took something like an hour. And this will close the gap between the index state, which was created by the offline reindexer, and the ongoing development, which developers will still create new changes, upload new patch sets, do commenting and so on, which will create new objects which need to be reindexed, and this will be taken care of by the online reindexer. What is still open is to automate the few manual steps which are still in the current version necessary to do an upgrade, but it's already helping a lot. So most of the heavy lifting is automated. This is support for the Gerrit indexer resource, and we plan to close those gaps so that the operator can do this fully automated. Prerequisites to deploy Gerrit on Kubernetes. So what does this setup need? So first of all, we need read-write many volumes. So we use NFS, but you could also use other read-write many volumes. You need one of the supported ingress providers. We use Istio. And you need a global RefDB implementation with the corresponding backend. In our case, that's Cloud Spanner, because we use GCP. So this was a short recap of what is k8s-gerrit and what has been changed, what has been improved since last year. And Thomas gave a presentation on that. And now I want to go over the changes we did in order to migrate from what we did before. So at SAP, we have a fork of the Gerrit core repository and all the plugins we use. This ensures we can fix bugs quickly. And we added all the plugins as submodules to the Gerrit repo so that in the end, the Gerrit fork contains all the plugins we need. We use Jenkins to run the builds, and our setup is based on what is also used upstream. We deploy binaries to Artifactory, and for security scans, we use Mend. In the past, before the migration, we ran on-prem. So we had huge bare metal machines, which were partitioned using Linux resource groups, and we had running multiple Gerrit instances per machine. For automatic failover, we used SUSE HA cluster. So this was a scripted solution. Failover took something like 5 to 10 minutes. And we had a bunch of cron type entries to fetch configs, for example, Gerrit config, which is versioned in Git repo, also to run the Git GC incoming replication and also backup was all scripted. We ran stable releases, so we did typically an update to the next minor release 1 or 2 times per year. Often we were behind the latest release. We did upgrade preparation and testing of fixes and upgrades on a test instance, having a copy of the production data so that we can test with realistic content. And we had a manual process for doing a preparation of a new index version, which was quite time consuming. So the first step we took in order to prepare for moving to the cloud and to Kubernetes was to upgrade to master and do upgrade more frequently. The advantage is that if you run master, you typically deploy in small chunks, and smaller updates reduce risk. Typically, rollback is possible because changes are done, index schema changes are done in a way so that for some time rollback is still possible until too many other changes have been put on top of that. It reduces also heavily the effort to contribute upstream because you don't need to argue if your change can go to a stable branch or not. And it's also easier to consume new features when they get available instead of having to wait for the next release. We have some CI jobs which auto-merge upstream. So we run that daily or on demand, and those auto-merges are pushed for review by the CI. And then one of the developers looks into the merge, and if there are conflicts, we have to resolve them manually. And then, as soon as such a change is submitted, it will automatically be taken care of by the CI pipeline, which we also extended to build the container images and test them. And we also have a CI job which can prepare an update of our clusters to the next new version. Now, how do we run the Kubernetes clusters? We use Gardener to manage the Kubernetes clusters. That's an open source project run by SAP. It provides uniform certified Kubernetes clusters across many infrastructures. We use Google Cloud Platform. One advantage of using Gardener is that the Kubernetes control planes also runs as pods in Kubernetes, so they need less resources, and restarting control plane is much faster because it just means restarting a few pods. It also provides day 2 operations like Kubernetes and Linux upgrades, hibernation of clusters, certificate rotation, and so on. The worker nodes we run use Garden Linux, which is a Debian derivative, also managed by SAP. It's also an open source project. Then we implemented continuous deployment, first for the Kubernetes clusters and the cloud infrastructure. So we use the version Terraform scripts in Git repository. And via Gardener API, we set up the Kubernetes clusters and the worker nodes. And volumes, network, and managed services are directly set up by Terraform script. We have some jobs to do to run the backup and restore procedures. And we also have a disaster recovery job, which can set up a new cluster from a backup of one of the productive clusters. For the application itself, so k8s-gerrit deployment, we use Jenkins and Argo CD to automate the deployments. We have a deployment repository which we mirror to GitHub, and just in case there's a problem with Gerrit itself, so that we are still able to modify the deployment. It contains the cluster configuration, which versions to use, and it also sets up the logging and the monitoring stack we use. Config changes are reviewed in Gerrit, and as soon as such a change is submitted, it will be automatically deployed by the CI. And we also have a job which generates release notes. So this is nothing fancy. It's just creating the recursive Git log, so that you also know what's in a deployment if just some plugins changed. We use stage deployment. So we have 3 clusters: a dev cluster, where we only have configured little resources. So it's mainly used to test config changes and do functional tests for new functionality. This cluster is hibernated during the night to save costs. Then we have a stage cluster, which we use for acceptance tests. Also, stakeholders can use it to test new versions. And if we do perform the load tests, we can scale up the resources on demand. And then finally, of course, we have the prod cluster, which is used by the end users. And in order to propagate changes through these 3 stage clusters, we have a CI job which prepares propagation of changes done in dev to the other 2 clusters. For the migration from our on-prem setup we used before to Kubernetes setup, we use the mentioned Terraform scripts to prepare the clusters. First the infrastructure and then the Kubernetes cluster. Then we prepared the k8s-gerrit deployment. The initial config was based on the on-prem config from all the Gerrit configuration options. Of course, we had to adapt. We had to, in addition, configure the custom resources for the Kubernetes deployment. Then we transferred data backup from on-prem to GCP, which contains the Git repositories, the Lucene indexes, and also the persistent caches. Initially, we only set up the dev and stage clusters. So most of the testing happened in the scaled up stage cluster, integration tests, stakeholder tests, performance and load tests. And then we adapted config, fixed bugs, rinse and repeated for 3 months, roughly. And then finally, the productive migration happened on a weekend during a 1-day downtime. We kept our fingers crossed and it worked, but we had quite some issues afterwards. And in the remainder of the talk, I will go through these issues and what we did to mitigate them. So first and worst one was a known bug in Envoy, which is the proxy used by Istio to provide proxies into every pod to manage the network connections. Envoy proxy doesn't update the IP address of restarted pods. And we didn't notice that in the test because we didn't have pod restarts in the tests. And those pod restarts, which we then faced in production, were caused by failing liveness probes, typically by, for example, if memory pressure was too high, then the health check failed, and then Kubernetes restarted the pod. And afterwards, HA plugin couldn't propagate events to the restarted pod. So the consequence was that most of the time, event propagation worked only in one direction, and the effect for the users was Lucene indexes diverged and the UI went crazy. This was fixed by adding service entries, which was recommended in some issue. We had issues also with the index sync. So still, after this was fixed, we still had incoherent index data in the primaries, which were caused by sporadic pod crashes. We added a background index sync, which runs regularly on a regular schedule to index changes which were recently indexed on the other pod. So on a pod restart, it will reindex the changes updated during the last 1 hour. And after the pod restart was done, then it's checking every 5 seconds for all the changes which have been updated during the last 5 minutes in the other primary pod. We had also fun with sticky sessions. So we started out with cookie-based sticky sessions to mitigate UI issues. If your requests are load balance round robin, then due to async indexing and so on, there are some funny effects in the UI. So we used cookie-based sticky sessions, but then we learned that also REST API can have issues caused by asynchronous indexing. And finally, we mitigated that by switching to client IP-based sticky sessions. This avoids these issues with the REST API, but it has the disadvantage that the load on the primary pods can be a bit unbalanced, especially if there are large CI systems behind a single IP address. We also faced some issues with stream events. So clients use SSH stream events to consume events. For example, CI systems use that to trigger builds. And the problem was that restarts of the Gerrit primary pod can cause lost events, which means that builds are not triggered. We mitigated that by adding the events log plugin, which stores the events for 2 days, and clients can then replay the lost events. This is supported by the k8s-gerrit trigger plugin, for example. We also had issues with NFS. So on NFS, traversing a large number of files is slow. So we enhanced the gitgc script, adding features which are missing in JGit and gitgc, namely removing empty directories when loose refs get moved into packed pruning stale incoming pack and index files, which can be caused by interrupted push. So if a push request crashes or is stopped by pod restart. And there's also there can also be stale keep files, which are left over by interrupted push. And we started an improved re-implementation in Python. So this is still ongoing. The goal in the end is to implement these missing features, at least in JGit, maybe also in gitgc, so that more and more of this additional functionality is needed anymore in this wrapper. And we also had some fun with Java GC. So we faced sporadic slow requests on primary pods mostly, which were caused by Java GC, sometimes very high CPU usage. And this was already observed on-prem, so some of what I tell in the next slides was already done on-prem. So we tested all the available Java GC algorithms. First, parallel GC, which is known to have the highest throughput, so it's the ideal candidate to be used on Gerrit replicas. The problem they faced was that sporadically we saw very long young generation pauses. So they went up to 30 seconds almost. And after a lot of tracing with the SAP Java team, they fixed it in OpenJDK 21. And since then, those pauses are at most 3 seconds in our setup. We also tried G1GC for the primaries. The G1GC can reach shorter pauses than parallel GC, but we found out that it has issues with humongous allocations. So this is one example. On the left side, you see one allocation which was 93 gigabytes, and this caused a pod restart. So it was just Java. G1GC wasn't able to cope with that. And finally, we upgraded to Java 21, which brings generational ZGC, and that is the ideal selection for Gerrit primaries. So it needs quite some CPU, but it can reach very short pauses. So in our setup, it's less than 1 millisecond. And it doesn't have issues with large allocations, so we use it for Gerrit primary pods. So this is the configuration we currently run. So in case you want to try that, you can get the values from here. Let me summarize. So what are the benefits after using that for half a year? One learning is running master is a big plus. I mean, it requires quite some work to automate merges and implement a CD environment so that deployments are automated mostly. And another learning is that Kubernetes really helps to automate everything. So the basic principles of self-healing, so that, for example, that unhealthy pods are automatically restarted, really helps stability. It provides a means to have zero downtime rolling updates for Kubernetes updates, for Linux updates, for application updates, and also for configuration changes. Compared to the old setup, this makes the life of those running the system much better. Also, what we also improved on that journey was that now we have all configuration, including the infrastructure, completely under version control. What we also learned is that analyzing problems after you learned how to use K9s and how Kubernetes works, it's really easier than doing that on-prem. And another advantage is that adding a managed service or any tools you might need for diagnosis or improving monitoring and so on is easier than setting this up on-prem. And finally, Kubernetes setup helps to reduce the lock-in. So if you happen to need to move to another cloud infrastructure, the main things which need to be changed if you do that are the managed services, storage, because the concrete NFS configuration and so on might be different, and some of the infrastructure procedures might be different, but all the rest is mostly infrastructure agnostic. Here's some links where you can find the project, and there's a Minikube setup, which really is easy to use. So feel free to try it out to get an idea, to get some hands-on experience how this looks like. And of course, in the end, contributions are welcome. Okay, so I'm at the end. Are there any questions?
Yeah, Matthias, I don't know if you should be able to see the Q&A tab. There's questions in there, and then I think some people had some questions in the chat as well.
With running master branch directly, no concerns about regressions. Of course, there could be some bad commits in updating changes from, let's say, the last week. So far, it didn't happen to us, and no major regressions. Sometimes there were some small issues, but the main advantage is if you're running master and an update isn't good, you can simply roll back. So you can simply deploy the previous version. That typically works because the amount of changes between those updates is so small that you can simply roll back. Next question. You said you use a k8s-gerrit fork. Do you port the changes in the open source version of the repo, or you keep them internally? No, typically we do all the changes upstream, and we only have the fork in case we need to quickly fix something where we just can't wait for feedback from the community. But most of the changes, 99%, at least 99% of the changes we first do upstream. In addition, for the Gerrit setup itself, we have some internal plugins, and of course, those are not upstream because they're also not open source. How long-lived are the sticky cookies? Few minutes, few hours. This depends on. We don't use cookies anymore for sticky sessions, so actually, I don't know. And the improved GC script, that's open source, so that's in the old one based on Bash. Is in the k8s-gerrit repository. In the GC container, there's a script. And the new one is in the contrib folder of the Gerrit core upstream, but that's still in review. Okay, if there are no more questions, then thank you for your attention.
There's another tab next to chat, should say Q&A.
Okay.
Even more questions.
Didn't see that. Which framework do you use for performance and load testing? We have a simple scripted setup, which is using some Python scripts. I think that's also open source. I think Thomas pushed it also to Gerrit review. It's just some simple Python code, and it's also running in a separate Kubernetes cluster, which we just only spin up when we run a load test. It's trying to simulate what a developer does, and you can by using Kubernetes you can easily run many clients. So we typically run something like 20 clients, just to put pressure on the system. It's nothing fancy. So with Gatling you can do more detailed stuff. What do you use for cache management? We just use the built-in caches, which are based on caffeine. We thought about shared caches, but that's something for the future. So far, we didn't work on that. Luca asks if we use push replication or pull replication. Actually, since the setup we use, what I described, uses collocated replicas, those collocated replicas have direct access to the same file system like the primaries use, so there's no replication involved with that. But we have another replica deployment where we replicate all the changes to just as a live backup. And that is using still pull replication, but we plan to change that to pull replication. Currently, we use push replication, but we want to move to pull replication because it's faster and needs less resources. Any objection in moving to Java 21? No, I would recommend it. Because typically in every new Java version, at least performance is better than in the previous one. That's our experience. And in case you need a fix, it's easier to get it on the latest version. Luca mentions that he added the removal of the empty directories. I didn't notice because we still use cgit to run git.gc. NASA asks, did you consider any of the other HA-friendly event plugins? No, we didn't, because we use the high availability plugin also in another deployment we have for our customers, so we were already familiar with that. For replication, we use HTTP. So there was a question if we use HTTP or SSH for replication, we use HTTP. And the Apache receiver doesn't support SSH. So it's basically Apache web server plus some CGI scripts, and they only support HTTP. Why do you limit to only 2 primaries in the HA cluster? Basically, that was a limitation in the high availability plugin from the past. In the meantime, I think we only need to remove this check, and it should work. And we should also switch from using direct HTTP to send events to the other primaries to use JGroups instead, which can also use UDP, which is more efficient to distribute the same events to many other pods instead of having one-to-one communications between all the primary pods.
I think that was everything. Thanks, Matthias.
Yep.